We are going to be using the Newton sum to relate the following power sums to elementary symmetric polynomials, and then from there we solve for x, y, and z. So we're going to take the first equation, x plus y plus z equals to 4. So this is good all by itself. So we're going to move on to the second equation, x squared plus y squared plus z squared equals 38. So the Newton's identity for this is x plus y plus z all squared minus 2 xy yz and xz, right? And don't forget that this is equal to 38. Now x plus y plus z equals 4, and right here we have x plus y plus z. So basically we can replace this with 4 squared minus 2 xy plus yz plus xz equals 38, and this is going to be 16 minus 2 xy yz plus xz equals 38. And when you solve this, you have xy plus yz plus xz equals negative 11. That is sorted. Again, we'll have to keep this because we'll be needing it later on. The last equation is x to the power of 3 plus y to the power of 3 plus z to the power of 3 equals 106. So the identity for this is x to the power of x plus y plus z to the power of 3 minus 3 x plus y plus z multiplied by xy plus yz plus xz plus 3xyz, and this is equal to 106. Again, we can see that x plus y plus z is 4, so we have 4 to the power of 3 minus 3 times 4, okay, and then xy plus yz plus xz is negative 11, so we have negative 11 plus 3xyz equals 106. Now when you go on to do this, if you simplify this, we have 64 plus 132 plus 3xyz equals 106. And then when you do all of this, you have 3xyz equals negative 90. Now that brings us to xyz equals negative 30. Okay, so if you look at the first one, the second one that we have here, and then the third one, we can see that we have a kind of relationship we find in the symmetric roots of polynomials, of cubic polynomials, right? And so we can actually project x, y, and z as a root of some given equation. So let's say that x, y, and z are roots. X, y, and z are root of some cubic equations. It means that q minus x, now we are trying to form a new cubic equation, q minus y and q minus z equals 0. Now when we expand this, we see that q to the power of 3 minus x plus y plus z q squared plus xy yz xz q minus xyz equals to 0. And x plus y plus z is what we have here as 4. Xy yz and xz is what we've obtained as negative 11, and xyz is what we have here as negative 30. So we can simply replace each of them by their values, right? So we have minus 4q squared, okay, then minus 11q because this is negative 11, and lastly we have a xyz is negative 30 times negative, so you have a positive 30 equals to 0. Now if we go on to factorize this, we're going to be having q minus 2 q plus 3 and q minus 5 equals to 0. Now if we put this side by side with what we wrote here originally and then we compare, we have q minus x, q minus y, q minus z equals 0. If you compare, you're going to see something that x, if you compare, we have x equals to 2, we have y equals to 3, and then we have z equals 5. Oh, y equals negative 3 and z equals 5. Okay, but one thing is that either of x, y, and z can take any position here at any point in time. That is, here we could have this written as y and this written as x, and this is z, and in any pattern this could be z, this could be y, and this could be x, etc., which is basically permutations, right? So the other solution to this problem are going to be the permutations of all of the results we have here. So we have 2, we have negative 3, and then we have 5. As we've said, that x, y, and z can take on any of those values in the particular order. So which means that the next one can be 2, 5, and negative 3. Okay, and then we could have negative 3 at the top, then 2 and 5. Again, we could have negative 3 at the top, we have 5, and then we have 2. And lastly, we could have 5, negative 3, and then we have 2, and 5, 2, and negative 3. So these are the possible value of x, y, and z. So basically, these are more like a symmetric permutations of the results that we initially obtained. So thank you.